Hello everyone. Thank you Mustafa and the other organizers for asking me to give these talks. I would have loved to come to Turkey in person to give them, but that does not appear to be possible anytime soon. So my lectures will focus on the basics of complex geometry and Kähler geometry, heading towards the statement of the Calabi conjectures perhaps. I hope to give you some examples of where the Calabi conjectures are applicable, at least where the hypotheses are met, and hopefully we can spend a little bit of time on the proofs, but I'm not so optimistic about the latter. Nonetheless, so the background, I assume, is a strong knowledge of complex analysis and manifold theory in general, and also Riemannian geometry. Some functional analysis will definitely help. PDE expertise also will help if we get to the proof, but in any case, some of the other lectures seem to require some expertise in these areas anyway. Nonetheless, let's see how this goes. Okay. So if you already know what complex manifolds are, perhaps at least the first couple of lectures will be quite trivial. In that case, I apologize. Alright, so let's start. So let's talk about the end game. I mean, why should you care about the Calabi conjecture, or for that matter, about complex differential geometry at all? Yeah. So complex manifolds, whatever these objects are, I'll define them soon. They provide an interface between algebra, in terms of algebraic geometry, and number theory. Modern number theory uses the language of algebraic geometry heavily. It's not immediately obvious that it actually uses complex numbers as much and differential geometry as much, but it does. And analysis, that is differential geometry, PDE, etc. Okay, so complex manifolds lie in the interface between these subjects. So there's a lot of back and forth going on. There are some results in say complex differential geometry whose only known proof is via characteristic P methods, no less, and vice versa. Yeah. All right. So in particular, the Calabi conjectures, Calabi made several conjectures, some of which we'll discuss in this lecture series. They have many applications in algebraic geometry. Some of these words may not make sense to participants who have never seen these things, but that's okay. The whole point of this slide is to convince you that these things are actually useful. Yeah. So for instance, CP2, which is an example of a complex manifold, is rigid in the sense that anything diffeomorphic to it is biholomorphic to it. And whatever these words means, it's very clear that there's a very strong statement. Okay, and it has nothing to do with PDE, right? The statement has nothing to do with PDE, but the proof does. Fano manifolds, which as you can imagine are special kinds of complex manifolds, they're simply connected. Now the Fano condition is an algebraic condition. You can easily write examples of things that are Fano, but they are simply connected. That's a topological property, and the proof once again goes through differential geometry and PDE. The Bogomolov-Miyaoka-Yau inequality is an inequality between Chern classes. Again, if you don't know what they are, don't worry about it. But whatever they are, they're algebra geometric quantities. You can compute them without too much difficulty, and they satisfy an inequality in many situations. Okay, that can be proved using these things. Moduli spaces. Well, what are moduli spaces? Suppose you consider the set of all triangles, right? Now what's a triangle determined by? It's determined by, let's say, the length of its sides, yeah? So you need three numbers, well, more or less up to some symmetries, etc. So these three numbers it's not just a set, it has a structure in its own right? And it's important to study the structure of the set of all the things that satisfy a certain constraint. That's a philosophy in algebraic geometry which is useful for various things. I hope to give you at least one example soon. Now, Riemannian geometry studies Riemannian metrics on smooth manifolds. Since I am already assuming a strong prerequisite in Riemannian geometry, I assume you know what Ricci curvature is. So, surprisingly, the question of come up with an example of a Riemannian metric on a Riemannian manifold whose Ricci curvature is 0, but whose Riemann curvature tensor is not 0. That's not a trivial question to answer, and at least as far as I know, until Yau proved one of the Calabi conjectures, the answer was not known to be in the affirmative. Yau indeed came up with such an example, right? And surprisingly, this comes from complex geometry, right? Alright, so this is at a very broad level. Let me try to make some part of the motivation much more concrete and elementary. So in high school geometry, it can't get more elementary than this. So what questions do kids learn? How many tangents are common to two circles? Well, that depends on how the circles are oriented and so on and so forth. What kind of conic sections are there? Meaning that if you take a cone and you cut it with a plane, what kinds of figures do you get? Okay, you can get ellipses, hyperbole, etc. Yeah. Now, these sorts of questions can be studied using ordinary Cartesian coordinate geometry. Yeah. If you abstract out the philosophy behind these two questions, the first question is, how many objects, namely tangents, are there in Rn, in this case R2, satisfying certain conditions common to two given circles? The second question is, what is a conic section? Well, what is a cone? Well, what's the equation of a cone? Z equals x squared plus y squared, yeah? What's a conic section? You take this quadratic and you intersect it with a plane, right? So you get another quadratic constraint. So essentially you're asking me, if you take a quadratic polynomial in x and y, you set it to 0, what sort of geometric figures do you get? Classify them, right? So for quadratics we know the answer. For cubics, this problem was studied by Newton, no less, a long time ago. And he did a brilliant analysis of this sort of a classification for cubics. But beyond that, it's a hard question. Yeah, the answer is not known even to this date. The problem is these questions, while they're extremely beautiful, are very annoying in the real category. What do I mean? If I take x squared plus y squared as minus 1, this set is empty, right? So let's and x squared plus y squared is 0 consists of the origin, and x squared plus y squared equals 1 is a circle, right? So depending on the sign of your number on the right hand side, you get very, very different sets. On the other hand, if we use complex numbers, then x squared plus y squared equals minus 1, 0 and plus 1, they're all on the same footing. Okay? Similar kinds of answers are expected in all three cases. Now this is cheating. Yes, the really interesting question, something that even Euclid will be interested in, would have been interested in, is the real version of these questions, but it is hard to answer them. So we make a compromise by studying similar questions with complex numbers, right? Mind you, the subject of the first question, how many objects in Rn satisfying certain conditions, that's called real enumerative geometry, and it's certainly a difficult and a beautiful field, and a lot of work is being done even in the second question. So real algebraic geometry, right? But we won't deal with such questions. Our study is focused on the complex setting, this complex algebraic geometry, right? Now there's another motivation arising from number theory. So if you look at the circle x squared plus y squared equals 1 and ask what the rational points on the circle look like, meaning x and y are rational numbers, This is precisely the study of Pythagorean triples, namely things like 3 square plus 4 square is 5 square, right? I mean, you want to find all right angle triangles whose sides are integers. These two are equivalent. It's not hard to see by clearing the denominators. Now the point is, this circle, this locus x square plus y square equals 1 makes sense even when x and y are real numbers or even complex numbers. Or for that matter, if x and y are in some finite field, right? So there is a way to make to study all of these things simultaneously, that is through the mechanism of schemes, which we won't get into. But the bottom line is, since you can make sense of it over R2 and C2, you can try to throw differential geometry at this problem. It won't really work. This was just a sort of a proof of concept, as in principle this sort of a thing could be useful. That's all I'm saying. I'm not saying that Pythagorean triples require anything as fancy as differential geometry. It's very elementary. But the point here is, if you take Diophantine equations, they can define geometric objects, and you can try to do differential geometry on these objects and hope to get something number theoretic out of them. Okay, this approach is called Dirichlet geometry, and it has been fruitfully applied in many cases, for instance to prove the model conjecture in number theory. So I hope I have convinced you that studying geometric objects arising from complex numbers is a useful activity, not just in its own right, but it's a natural question coming from various other natural questions. Yeah. So without further ado, let's jump into the main topic. So all of the above forces us to study the loci of polynomials with complex coefficients, or more generally, of analytic functions in Cn. Yeah. So the resulting objects are usually manifolds with an additional structure on them, right? Alright, so finally we come to the definition of our main object of study. A complex manifold is a smooth manifold first and foremost, which is locally diffeomorphic to an open subset of Cn, as is expected, such that the transition maps, meaning the gluing maps between two different open subsets of Cn, are biholomorphisms, meaning they're holomorphic and their inverses are holomorphic too. Now the first question is, what the hell is a holomorphic function of more than one complex variable, right? You can imagine that there could be many ways to define this sort of a concept. They're all equivalent thanks to Hartog's deep theorem. So the one we'll adopt is this. So a holomorphic function is first and foremost a C1 function, and it satisfies the Cauchy-Riemann equations in each variable separately. Namely, it's separately holomorphic in each variable. What is another way to define it? You can say it locally admits a power series expansion, or perhaps you drop the C1 condition and you merely say it's holomorphic in each variable. All of these are equivalent. These sorts of things are spectacularly false in the case of smooth functions, but they are true in holomorphic functions. By the way, the meaning of this notation, df dz bar, it's simply half of df dx plus square root of minus 1 df dy. And recall that even in one variable complex analysis, you can neatly express the Cauchy-Riemann equations as df dz bar equals 0. Yeah? Why is there a half? That's for a technical reason. Okay, I'll come to it in a moment. Alright, so in principle we can go ahead and try to give examples of complex manifolds, but it's really not a good idea to not know about subtleties of holomorphic functions in more than one complex variable. They're not as straightforward as just a jazzed up version of the single variable case. Yeah. So if you have two or more variables, holomorphicity is very different from what you expect. For example, and this phenomenon is called Hartog's phenomenon. If you take a holomorphic function on Cn minus the origin where n is greater than or equal to 2, it can always be extended holomorphically to all of Cn. This should be shocking because, for instance, if you take n equals 1 and you take 1 over z, that cannot be extended all the way to C, right? It has a singularity at 0. So what this phenomenon indicates is that the singularities of holomorphic functions in more than two variables cannot be isolated, cannot be simply isolated points, right? Here's another shocking fact. The product of the disks is not biholomorphic to D2, the ball in two-dimensional space. That's not the case in the diffeomorphic category, for instance. Right? By the way, this sort of a thing can be proved by calculating the biholomorphism groups, I think using Schwartz lemma, some such thing. So several complex variables is a rich and difficult subject. Okay. So as for examples of complex manifolds, the most trivial example is of course an open subset of Cn. Already in this trivial setting, there are lots of features that arise with the presence of the complex numbers here, right? If you just think of Cn as R2n, then you'll simply say, oh, all right, I mean, what's the big deal? I mean, it's just R2n, right? But that's not it. There's more to it. For example, if you take Cn as R2n, you have the usual tangent space, right? What does the tangent space consist of? It consists of, it's a vector space that is generated by the bases d by dx and d by dy, right? Now, there is a notion called the holomorphic tangent space, which is denoted as T10. That's the complex vector space, not real, complex vector space generated by d by dzi. What's d by dzi again? It's half d by dxi minus I d by dyi. Right? So it's an n-dimensional complex vector space. So in particular, it is isomorphic to Cn itself. Right? And if you want to get a more geometric characterization of it, if you take any holomorphic map from C into Cn, its derivatives generate the holomorphic tangent space, the derivatives at the point P, at the point, the origin, for instance. Right? Just like if you want to talk about the real tangent space, you take equivalence class of curves, right? Here too, it's the equivalence class of curves, except these so-called curves as analytic functions from C to Cn as opposed to R to R2n. Okay? Right. Likewise, we have T01. What is T01? It's a vector space generated by d dz bars. And the dual of T10 is omega 10, meaning it consists of vectors generated by dz as opposed to d by dz. What is dz? dz is dx plus square root of minus 1 dy, right? By the way, this is the reason why there's a funny half factor in the definition of this. You see, you want dz acting on d by dz to be equal to 1. Now dz is dx plus square root of minus 1 dy. If there was no half in the definition of this, you would have gotten dz acting on this being 2. Okay, that's why you have a half there. Alright, so the dual of T01 is omega 01, namely its forms, complex forms generated by dz bar. Right? Okay. Basically, these things, the dz's, are simply, if you take R2n and you take its tangent space and complexify it, that is, you take complex vector fields, it's a subspace of that space. Likewise, this is also a subspace of complex vector fields. Okay? Complex tangent space, that is. Okay? Continuing along this theme, you don't just have 1, 0 and 0, 1 forms. By the way, these duals are called 1, 0 forms and these are called 0, 1 forms. More generally, you have PQ forms generated by dz dz1, wedge dz2, wedge so on until dzp, wedge dz bar 1, wedge dz bar 2, wedge so on until dz bar q. That's an example of such a form. You can take any multi-index with p as its size and q as the size of j. Okay, and you get lots of such forms. I think there'll be n choose p times n choose q in number, unless I'm mistaken. So these forms generate a vector space that's called PQ forms. Okay. Now if you have the exterior derivative, remember in usual differential geometry you have the exterior derivative which takes a k form and spits out a k plus 1 form. The formula being d omega is, if you write it, omega is f times dx1 wedge dx2 so on, then d omega is simply df dxi wedge the rest, right? So this exterior derivative breaks up into a sum of two differential operators called del and del bar, d equals del plus del bar, in the obvious way. For example, rather than defining them, or maybe I'll recall the definition later when we need it, it's as simple as simply saying if I want to compute del bar of this quantity, I take d by dz bar of this thing, wedge this. So d by dz bar of z1 bar, d by dz1 bar of z1 bar is 1. So it's 1 times dz1 bar wedge dz2 bar. dz bar 1 dz bar 2 is 0, so it's plus 0 times this, and so on. Okay. So that's the, I haven't defined del and del bar, as in when we need them I'll recall the definition more rigorously, but you can imagine what it is, right? It's a fairly obvious generalization of this example. And one can easily see that del square and del bar square, they're both 0. Okay, if you look at the definitions. So in Rn we have the Poincare lemma. Namely, if you take any contractible open set, for example a ball or all of Rn for instance, if you take any closed form, namely d omega is 0, they're all exact, namely omega is d eta, right? You have similar del bar and del Poincare lemmata in Cn, except you have to be careful. These things are not true for any contractible open set. So that's why whenever I say the Poincare lemma, I'm usually referring to on a ball. Okay. So basically what these things say is that if you have a ball in Cn and you have a PQ form on it, such that del bar of this PQ form is 0, then this PQ form is del bar of a PQ minus 1 form. Likewise, if you have a PQ form and its del is 0, then this form is del of a P minus 1 Q form. Yeah? So basically I'm merely saying that there is an analogy between the usual Poincare lemma and these things for balls, at least, not in general, for balls. Okay. So now we return back to our original question of producing examples of complex manifolds. Enough of these several complex variable things. But before we do that, we need a key tool. How do we produce examples of our good old smooth manifolds? What's your favorite example? You can take your favorite function like x square plus y square and set it equal to 1, right? More generally, take your favorite function, set it to 0, and hope that the 0 locus is indeed a manifold. For this hope to hold true, you need the implicit function theorem, right? You need a condition on the derivative. So you have the same machine here as well. So you have an inverse function theorem first in the holomorphic context. That is, suppose f from Cn to Cn, you don't need it to be defined on all of Cn, you just need it on an open set, but I didn't want to state that. So if you have a holomorphic map between Cn's, And if the derivative at say 0 is invertible, then locally near 0, f is a biholomorphism. What does that mean? There's a neighborhood of 0, u, such that f of u is an open set in Cn, and f restricted to u, from u to f of u, is a biholomorphism. By the way, it's not very hard to prove this theorem. Basically, the fact that the derivative is invertible means that the usual inverse function can be applied to conclude that f is actually a local diffeomorphism. Now, how do you know whether a diffeomorphism is a biholomorphism or not? Well, that's as simple as asking how do you know whether a smooth function is holomorphic or not. What will you do? You will simply take del bar of the smooth function and check if it's 0 or not, right? And of course, if you take the inverse of this local inverse of the resulting, the local smooth inverse, the chain rule will tell you that its del bar is 0. Okay, so it's actually fairly easy to prove this inverse function theorem given our usual inverse function theorem. Okay, you don't have to go through the proof of that again. Alright. So sorry for the typo here. So once we have an inverse function theorem, we have an implicit function theorem, and we have a constant rank theorem. All the usual multivariable calculus applies, right? So what does the implicit function theorem say? We have a map from Cn plus m to Cn, and the derivative, a part of the derivative matrix is invertible, then the rest can be solved for in terms of these things and so on, right? So yeah, so that's that. Alright, so before we come to examples of complex manifolds, again one last definition. What's a complex submanifold? It's a complex manifold in its own right. It's a subset of M, such that the inclusion map is a holomorphic embedding. Well, what does that mean? Unfortunately, I've defined holomorphic maps between complex manifolds later, but let me just state that right away. Basically, what is a holomorphic map between two complex manifolds? It's simply a smooth map, such that if you choose complex coordinates here and complex coordinates there, it's a holomorphic map. Okay. If it's true in one set of complex coordinates, it's true in all the other complex coordinates because you change them only by means of biholomorphisms. Okay. So a complex manifold is simply a smooth submanifold, except the inclusion map is not just an embedding, it's a holomorphic embedding. Okay. And just like in the smooth category, if you use the implicit function theorem around every point here, there is a holomorphic coordinate chart such that this is given by the 0 locus of the first few coordinate functions, right? Like for example, even in the smooth setting, how can you characterize submanifolds? You can always find nice coordinate charts where if you just set x1 equals 0, x2 equals 0, and so on till xk is 0, then you get the submanifold, right? In other words, the rest of the coordinates are actually coordinates on the submanifold. The same philosophy holds even in the complex setting. Okay. Alright, so the implicit function theorem implies the following very useful result, which also has an analogy in the smooth case. So if you have a holomorphic map between complex manifolds, which means, as I just said, in any pair of coordinate charts, this is a holomorphic function. If P is a regular value for this map, what does a regular value mean? A holomorphic map is in particular a smooth map, right? We know what regular values for smooth maps mean. What do they mean? Well, if you take the pre-image of P, it's a set of points in M. At every point, the derivative of this map is surjective, right? That's what a regular value means. And by Sard's theorem, most values are regular values, right? The set of critical values has 0 measure. Yeah. Anyway, so if you have a regular value here, its pre-image, as you can imagine, is a complex submanifold of the correct dimension. This is simply saying if you take, suppose n is just say Cn, right, and m is just say Cm. All you're saying is you're setting n functions to 0 in Cm. So you have n equations and m unknowns. So the number of free parameters ought to be m minus n, which is exactly what this is. Okay. Alright, so finally, as promised, we come to examples of complex manifolds, non-trivial ones, other than just open subsets of Cn. So if you take x square plus y square equals 1, in R2 it would have been a circle. In C2, it's a complex manifold. Why? Because x square plus y square minus 1 is a holomorphic function. Why is it a holomorphic function? Because if you take, it's differentiable in x and y separately, right? It's complex differentiable in x and y separately. Its complex gradient is 2x comma 2y, and it's not 0 comma 0. That means the real gradient is also not 0 comma 0. By the way, this is a point I glossed over. I invite you to please find out what the relationship is between the real derivative matrix and the complex derivative matrix for a holomorphic function. Okay. Yeah, so please do that as a little exercise. Anyway, so the complex gradient and hence the real gradient is not 0, 0. I mean, of course it is 0, 0 when x and y are 0, but that point doesn't lie on this, right? So this is an example of a complex submanifold of C2. The small twist here is that it is not compact. Well, obviously, if y is allowed to be arbitrarily large, you can still solve for x. Yeah. So, in fact, there are no compact complex submanifolds of Cn. Yeah. This is a fact. So, unlike in the real category, there are no compact complex submanifolds of your favorite space at all, right? So already it's a non-trivial question to come up with even one example of a compact complex manifold. And our entire lecture series is devoted to compact complex manifolds, right? So already it's a little interesting here. So this fact that there are no compact complex submanifolds of Cn can be proved using a more general fact. Okay, the more general fact is if you have any holomorphic function on a compact, by the way, all our manifolds are connected. I'm not going to repeat this again. Okay, any holomorphic function on a compact complex manifold is a constant. This should be shocking, right? I mean, you can always produce lots of examples of smooth functions on your favorite compact smooth manifold, right? Using a bump function example, right? But holomorphic functions are very hard to come by. On compact complex manifolds, only constants are holomorphic functions. But before we set out to prove this little fact, why do you think this fact implies that there are no compact complex submanifolds of Cn? That's because if there was a compact complex submanifold, you restrict the coordinate functions of Cn to that submanifold. They'll all be holomorphic functions. Restrictions of holomorphic functions are holomorphic. So they're all constants. That means all the coordinates of every point on this manifold are all the same. I mean, they're all constant, which means it's simply a constant, which means it's simply a point. I mean, maybe I should have said that the only compact complex submanifolds of Cn are points. That's the correct statement. This is a slight inaccuracy, but I hope the essence is appreciated. Alright, so coming back to this, how would you prove this sort of a fact? Suppose you take u is a real valued function on a compact topological space, so it achieves its maximum at a point. Now here comes the punchline. if you take the real part of a holomorphic function in one complex variable, it's harmonic, meaning the Laplacian of it is 0, right? The same holds true for the real part of a holomorphic function in more than one variable, and that is true even on a complex manifold where there is no fixed coordinate chart. I invite you to please verify that if you take a holomorphic function on a compact complex manifold and you choose any coordinate chart, U is harmonic in that coordinate chart. It does not depend on what coordinate chart you choose, as long as it's a holomorphic coordinate chart. Okay, so this is already an interesting fact, right? Alright, so since U is harmonic, well, what do we know about harmonic functions? Well, if you don't know this fact, I invite you to look it up in Gilbag and Trudinger's book. It's not very difficult to prove. Harmonic functions satisfy the mean value property, meaning their value at any point equals the average over a ball centered at that point. So if the maximum is achieved at the center of the ball, that means the function has to be constant, right, on the entire ball. And a simple connectedness argument then shows that it's constant throughout the manifold. Okay. Alright, so already we have a non-trivial and a very fascinating fact. There are no compact complex submanifolds of Cn. So how the hell do we come up with examples? Well, how do we come up with examples even in the smooth setting? Like, suppose I forbid you from coming up with submanifolds of Rn, what will you do? Well, you can't do anything because by the Whitney embedding theorem everything is a submanifold of Rn, but forget that. How would you come up with examples? The quotient construction, right? So the simplest example of a smooth manifold that's not obviously a submanifold of Rn is a torus, right? It's obtained by Rn quotiented out by a lattice. The same principle applies in the complex setting. Suppose you take Cn and take your favorite lattice. For my favorite lattice is Z2n, the standard lattice. That is, you take the standard basis of R2n and take all integral linear combinations of that basis, right? So you get a lattice, quotient out Cn with this lattice. Basically, you're taking R2 and quotient out by lattice, so you get something that's diffeomorphic to S1 cross so on until n2n terms. So it's a compact smooth manifold of dimension 2n. The fact that it's a complex manifold is also not very hard to see. You can easily come up with coordinates from Cn. Like, how do you prove Rn quotiented out by a lattice is a smooth manifold? You take the coordinates in Rn, and if you the change of coordinates is simply taking those coordinates and adding to them something, right? Simply an affine change of variables does the job. Likewise, an affine change of variables, which is always biholomorphic, does the job here also. You can easily prove that a complex torus is a complex manifold. Now this example is a little harder to see that it's a complex manifold, and I'll discuss this in a little more detail in a moment. So if you take all the lines, if you take Cn plus 1 and take all one-dimensional complex vector spaces through the origin, which I'll call lines through the origin, right? It's reasonable to call them that. This set can be endowed with a manifold structure. In fact, even in the real category, this is the case, right? If you take all real lines passing through the origin and in Rn, what do you get? Well, you can always talk about a real line through its intersection with the sphere, but every line intersects the sphere in 2 points, so you identify those 2 points. So you take Sn quotiented out by the antipodal point, so that's Rpn, right? Yeah. So akin to that, you have Cpn, the complex projective space. That is, you take Cn plus 1 minus the origin. What is the meaning of a line? I mean, when do you say 2 points belong to the same line? When they differ by a non-zero multiple, right? So this set is, as a set, it's a set of all lines. It turns out it's a compact complex manifold. The fact that it's a complex manifold is not too hard. I'll just produce explicit coordinates in a moment. The fact that it's compact requires a little bit of effort, and I invite you to put in that effort. A hint is that you should be able to show that it's diffeomorphic to S2n plus 1 quotient without by S1. The last example is the Hopf surface. You take C2 minus the origin, take this curious equivalence relation. You say Z is equivalent to Z, and to 2Z, and Z over 2, and 4Z, Z over 4, etc. It's not immediately obvious this is even a smooth manifold, forget a complex manifold. But I invite you to prove that this is diffeomorphic to S1 cross S3. So it's in particular a smooth manifold, a compact smooth manifold. And I invite you to come up with coordinate charts on this piece. Yeah. So we return back to our extremely important example of CPN. So to prove it's a complex manifold, you'll have to produce coordinate charts. Yeah. Now I'm going to denote, this is standard notation, the coordinates on Cn plus 1 as x0, x1, so on until xn. Right? So I'm going to start with 0 as opposed to 1. Okay. So suppose you take the open set in Cn plus 1 where x0 is not 0. That open set defines an open subset of CPN. Right? By the quotient topology you can see that it's still an open subset. Right? So suppose x0 is not 0, that's an open set. Define these complex valued functions on that open set on CPN as xi over x0. Now notice that xi over x0, namely I'm calling them zi. By the way, if you're used to Riemannian geometry, you will understand why I'm putting superscripts over these coordinates. Eventually I want to be able to use the Einstein summation convention. Yeah? Alright, so zi is xi over x0. These are this set of functions gives a homeomorphism between this subset of CPN and Cn. Right? If you choose another subset where not x0, say x1 is not 0, a similar collection of coordinates gives you a homeomorphism with Cn. So CPN is simply a bunch of Cn's glued together. And the transition maps, you can easily see they're biholomorphisms. There'll be something like the ratio of two holomorphic functions where the denominator is not 0. Okay? So I invite you to complete this argument, but this is an important coordinate chart. So I'm just talking about this particular one. Okay? These xi's, they're coordinates in Cn plus 1. They're obviously not coordinates on CPN, right? But they're confusingly termed homogeneous coordinates. Okay? The terminology is confusing, but it's useful, as you'll see soon. Now, with great difficulty, we have managed to produce 3 sets of examples. Yeah? How do you come up with more examples? Now it's not so bad. If you give me one example, I can produce lots of examples by considering sub-manifolds of this existing example, right? So we will consider submanifolds of CPN. They're the most interesting ones and the most numerous. Okay. So how do you come up with examples of submanifolds of CPN? It's not so easy, right? So here's a very interesting way to do that. So suppose you consider this plane in Cn plus 1 given by a linear polynomial, linear homogeneous polynomial set to 0, where this vector A is not 0 identically. So meaning that, for example, the plane x0 equals 0 is an example, x0 plus x1 is 0, etc. This is a priori a subset of Cn plus 1, but it also defines a well-defined subset of CPN. Why? Suppose you take something in its equivalence class, namely you multiply all of these by lambda. That will also satisfy this equation, right? So if x belongs to this set, the entire line containing x will satisfy this equation, right? So as a set, it defines a well-defined subset of CPN. But not all subsets are submanifolds. In this particular case, you can explicitly solve and show that it's a submanifold of CPN. In fact, it is biholomorphic to CPN minus 1. How do you show that? Suppose, let's say the A naught is not 0. Then you can solve for A naught in terms of the others, right? So consider this map from CPN minus 1, where the homogeneous coordinates are x1, x2, so on until xn, to CPN given by x1, so on until xn, goes to x0, x1, x2, so on until xn, where x0 is obtained by solving this. Right? That map can be easily shown to be a biholomorphism. You can explicitly do it. It's not rocket science. In a way, it's more fundamental than rocket science. Alright, so more generally, so what created the magic here? The fact that if x was in this set, lambda times x was also in this set. Well, how did that work? Well, we could pull the lambda out of the equation, right? So more generally, if you have a homogeneous polynomial, what does that mean? If you put a lambda in front of all of these, you can pull lambda raised to d, where d is the degree, outside. So f of lambda x is lambda raised to d times f of x. So if you take any homogeneous polynomial, its zero locus is at least a well-defined subset of CPN. Namely, if any point lies on it, the entire line in Cn plus 1 will lie on the zero locus. Right? So at least you have a well-defined subset. Now it's not obvious that, unfortunately, unlike this where you can explicitly solve, it's not clear that you can actually, this will always be a submanifold. In fact, it is not always a submanifold. That's not true. Okay. So for example, this particular beast, if you take the homogeneous coordinates on CP2 to be x, y, z, then y square x equals z cube is not a submanifold. Well, how would you see that geometrically? Suppose you look at the coordinate chart where x is not 0, then you have two coordinates z1 and z2. z1 is y over x, z2 is z over x. So z1 square equals z cube. If you look at the, in R3, in R2 for instance, this would have had a cusp at the origin, right? If you sketch it, it has a cusp. It looks like this, yeah, in R2. So you can very well imagine that it's not a submanifold, but you can also actually prove it. Okay. Anyway, the bottom line is it's not always a submanifold. So when is it a submanifold? So using the implicit function theorem, you can show, by the way, it's not immediately obvious. It's not an obvious application of the implicit function theorem. You need to do a little bit of work. You can show that if the gradient of this function is not 0 on the 0 locus in Cn plus 1 minus the origin, of course it's going to be, whenever I say 0 locus in Cn plus 1, I mean 0 locus in Cn plus 1 minus the origin. Okay, please forgive this typographical error. So if the gradient is not 0 on the 0 locus, for instance, what's the gradient of this beast? It's just the vector A, and this vector A is not 0. Okay? Then this 0 locus, which defines a well-defined subset of CPN, defines a submanifold of dimension n minus 1. That's the whole point. Okay? And there's not an obvious application of the implicit function theorem because these things are not really coordinates on CPN, right? They're coordinates in Cn plus 1. The gradient not being 0 on the 0 locus merely means that the 0 locus is a submanifold of Cn plus 1. How do you know that a submanifold of Cn plus 1, which defines a well-defined subset of CPN, is a submanifold of CPN? That's not obvious, right? That needs proof. So an easier way to do it is as follows. So how can you prove something is a submanifold? Well, if you around every point, if you can find a function, a holomorphic function locally defining it, such that its gradient is non-zero, then by the implicit function theorem, you're done, right? So suppose you take our favorite coordinate chart where x0 is non-zero. Assume that, so since we are assuming the gradient is not zero, df dxj for some j, it's non-zero, right? For now, assume j is not zero. That is, df dx1 is not zero, for example. Okay. In that case, so because this is a homogeneous polynomial, you can pull the x1 out. So this becomes 1 and this becomes these become the coordinates in CPN. So you get f of 1 comma z1 so on until zn is 0. Now if you take df dzi, so if you call this function little f, df dzj of this thing is df dxj, right? And by assumption it's not 0. So that means locally on this coordinate chart, this beast is actually a submanifold provided j is not 0. What happens if j is actually 0? It cannot occur. Namely, the possibility that df dzi is 0 for all I and df dx naught is non-zero, that cannot occur in this coordinate chart. Why? I'll leave that as an exercise, but the whole point is if you take any homogeneous polynomial, it satisfies a beautiful identity, Euler's identity. The identity is if the degree of this polynomial is d, then f times d is x0 df dx0 plus x1 df dx1 plus x2 df dx2 and so on. This particular assumption would then say that 0 equals something that was not 0. That's the contradiction. Okay. So at least on this coordinate chart, we see it's a submanifold. And similarly on the other coordinate charts, the same argument applies. It's just a permutation of these sorts of things. So, I mean, the argument is just a permutation of this argument, if I may say so. Okay. In the same vein, if you have a collection of homogeneous polynomials in Cn plus 1, their simultaneous zero locus is a well-defined subset of CPN. Please check this. Okay. This simultaneous zero set is called an algebraic set. If it is connected, it's called a projective variety. Okay. Actually, I'm lying a little bit here, or not lying. I'm taking the easy way out. An irreducible algebraic set is called a projective variety, but that's the same as this. Yeah, right? So not all projective varieties are manifolds. Well, why not? Well, here is the example, right? So which ones are manifolds? Well, in general, you can use the implicit function theorem style argument just like this if you have even more than one function. For example, if sum of xi square is 0, and that's also the sum of xi is 0, so you have two equations. This will be an n-2 dimensional submanifold by the same implicit function theorem style reasoning. If you take the complex gradient of this function in Cn plus 1, it's going to be 2x0, 2x1, so on. Complex gradient of this is 1, 1, so on, and these two guys are actually linearly independent. Yeah? And the same kind of reasoning applies. Alright. So now we have a machine to produce lots and lots of examples of compact complex manifolds. Namely, take a few homogeneous polynomials, like less than n homogeneous polynomials, take a regular value of all of them simultaneously, in the sense that you take a map from Cn plus 1 to Cr, where R is the number of such polynomials, and take a regular value of this map and pull it back. if that regular value happens to be 0, meaning is a complicated way of simply saying that if you set all those polynomials to 0 and if the derivatives are all linearly independent on the 0 locus, then it defines a complex n minus r dimensional submanifold of CPN. Okay, so now we can produce lots of examples of compact complex submanifolds. Now this procedure raises a very interesting question. Recall that in our usual in the real category, if you take any smooth manifold, it's a submanifold of Rn by the Whitney embedding theorem. We just saw that compact complex manifolds cannot be submanifolds of Cn. Well, are they all submanifolds of some standard space? In particular, are they all projective varieties? That's a very reasonable question to ask, right? Seeing that we are producing so many examples, unfortunately the answer is no. In fact, if you choose a torus of dimension greater than or equal to 2, by the way, all tori of dimension equal to 1, in fact, all complex manifolds, compact complex manifolds of dimension equal to 1 are projective varieties. Compact complex manifolds of dimension 1 are called Riemann surfaces. All Riemann surfaces are projective. Okay, that's a theorem of Riemann. But anyway, if you take a large enough dimensional randomly chosen torus, by randomly I mean genuinely randomly. You take the space of all tori and throw a dart at them. Right? You take a randomly chosen torus, or for instance, or if you take the Hopf surface, these are not projective. It's not obvious that they're not projective. It's a deep theorem. Well, at least this one is a little easier, but still it's not obvious. But they're not projective. Okay, so you have counterexamples, very simple counterexamples. So that raises the question, what compact complex manifolds are projective? Right? There's another interesting question. First of all, what compact complex manifolds can you embed in CPN? Secondly, which of them are projective varieties? Namely, which of them come from zeros of homogeneous polynomials? So these are two separate questions. I hope you understand this. One of them asks you whether you can embed the manifold in projective space. The other asks whether that particular submanifold comes in a particular manner by the zero of a homogeneous polynomial. It turns out, while the first question is of course false, these are counterexamples, the second is always true. If you take any compact complex submanifold of CPN, it always arises used by this construction. It's always a projective variety. It arises through algebra. Okay, so that's called Chow's theorem, and it's not easy to prove. In fact, Serre generalized these observations in his famous Geometry Algebraique, Geometry Analytique paper. So algebraic geometry and analytic geometry coincide on projective varieties. Okay, so that is the bridge. You see, you can study these using algebra, you can study these using geometry. So in particular, you can use geometry and PDE to help with algebra and vice versa. That's the bridge, really. Okay. Anyway, coming back to the first question, which compact complex manifolds can be embedded in projective space? That there's an if and only if criterion, the Kodaira embedding theorem, that tells you when this can be done. It's not trivial to check, but it's not very hard to check either. But it's not easy to prove, by the way. Even stating the Kodaira embedding theorem would require me to introduce more language. Very roughly, I hope everyone knows what vector bundles are and what line bundles are. This is part of the prerequisites that I'm assuming. So there's a notion of a holomorphic vector bundle and a holomorphic line bundle. I'll just define them later on. Basically, you are a projective manifold if and only if you admit a nice holomorphic line bundle. What does nice mean? Well, I'll define that later also. Nice simply means that you have a metric of positive curvature. But anyway, okay. All right. So so that's that. That's enough for this lecture. Just to recap, we've defined complex manifolds. Then we decided that we need to look at holomorphic functions of more than one variable in a little more detail. We did that, crash course if you will. We came back to complex manifolds, we asked for examples, we saw that unfortunately it's hard to produce compact examples because all complex submanifolds of Cn are trivial, they're all points. So to produce compact examples, we came up with three standard ones: tori, hop surface, and projective space. And then we came up with subsets of projective space, which are submanifolds. It's not very difficult to come up with such subsets. You take homogeneous polynomials and set them to 0, such that a derivative condition is met. Right? So, and then we asked if that's the only way to produce compact complex manifolds. Unfortunately, that's not the case. The other two examples we generated, many of them are not going to be produced this way. And there is a criterion to decide when your manifold is like this. Okay? Alright, so I'll stop here. Thank you for listening.